And thank you, the organizers, for inviting me. And it's an honor to be here. Sasha, it's a beautiful occasion. And I have to maybe admit that I learned a lot from Sasha, in particular, the way he sees things from above, this kind of vision, constructing bridges in between various areas of mathematics. And one particular thing that I would like to mention before I start our talk with Anton Zosimov is that I learned how to call the papers. So what would be the best title of a paper? Of course, it's very subjective, but I particularly like this one, Conwy River and Arnold Cell. It's a paper of Sasha with spotting, and this is about certain relation between domains in number theory that was promoted by Conwy in terms of quadratic forms and Arnold in terms of continued fractions. So these are exactly those domains. So Conwy River with which one constructs values of quadratic forms, and that's a nice picture of Arnold. Actually, all of this from Sasha's papers. So since we are talking about Arnold already, so I'll move on to the main subject of my talk, and this is about various ramifications of Arnold's equations, of Euler equations, and in particular in the setting that was promoted by Arnold. So let's take as a starting point a Riemannian manifold M. So I will so we take a manifold, we take a metric on it, so it's Riemannian manifold, but the volume form mu is not necessarily related to this metric. Now we'll describe fluid by means of Eulerian coordinates. So in other words, we have a domain and we do not trace any particular particle, but rather we look at how velocity field is evolved. So V will be the velocity field of the fluid, and it's supposed to be divergence free. The fluid is assumed to be incompressible, and then the evolution of this divergence free velocity field is described by the Euler equation that the material derivative of this velocity field is given by gradient of a function which is called the pressure function. It is defined uniquely up to an additive constant. So here the second term, this nabla VV, is the covariant derivative with respect to the Riemannian metric that is already on the manifold. So that's the setting, and then a beautiful theorem of Arnold of the middle of 1960s is that it turns out that the Euler equation is the geodesic flow on the group of volume preserving diffeomorphisms. So maybe just kind of save the pictures already here. I'll just repeat it, that the setting is much more general than it is given in this theorem of Arnold. So if you start with any Lie group, so for instance finite dimensional, then so that we take the corresponding tangent space at the identity, which is the Lie algebra, and then we fix one more ingredient, which is the quadratic form. So this will be a quadratic form. So this is the unit ball of this quadratic form. Then we move this to any other point of the group. So at every tangent space, we have its own unit ball. So this gives us a Riemannian metric on the manifold. Then given an initial velocity vector, we consider geodesic with this very initial vector with respect to the Riemannian metric that now is a right invariant metric on the group. You have a quadratic form at every point. And then given velocity vector at any point on the geodesic, we pull this back. It will not be the original vector. It will be in general a new vector. It would be the original vector if it were a one parameter subgroup. So in other words, if the metric were bi-invariant, but it will be some evolution of the velocity vector. And the Euler equation describes such an evolution with for given two ingredients, we have to fix the group and also the metric of the quadratic form on the identity. So it turned out to be a very, very general setting, as one can see in this table. So Arnold himself already showed this for rigid body, for the rigid body, and also for an ideal fluid for the group of volume preserving diffeomorphisms when you fix an L2 metric. But there are many other examples. For instance, Kirchhoff equations are for body in a fluid are given by this construction on the group of motions of three-dimensional space. For instance, on the Virasoro group, one can fix various metrics, L2, H1, H1 dot, and get various equations of shallow water, TdV, Kamasa-Holm, Hunter-Saxon equations. And there are other examples. For instance, MHD, so magnetohydrodynamics, is described by the group of volume preserving diffeomorphisms, semi-direct product with divergence vector fields. So there are, it turned out to be indeed a very rather universal point of view. And then there exists a Hamiltonian version of this when one considers this not on the Lie algebra but on the dual space. And also one can give its analytic setting. This was done by Ibn Marsden for the example of fluid, but then it was extended to many other settings, many other fluids, so compressible, for instance, and so on. So I would like to slightly change viewpoint, and instead of thinking of the group of volume preserving diffeomorphisms as so here we understand G as the group of volume preserving diffeomorphisms. Let's think about this group as a subgroup inside all diffeomorphisms. So here is the setting. So now I'm looking at the group of all diffeomorphisms of the manifold M. And the group of volume preserving diffeomorphisms that preserve the volume mu is just a submanifold in this group, this vertical fiber here. So we will look how this, we will observe how this group is fibered over the set of all probability densities on the manifold M. So on the density, I understand just a positive volume form, which is normalized by the condition that the total mass of this volume form is equal to 1. So we have all possible volume forms. This is a contractible space. This is the space here. It's the base of our vibration. So mu will be just one point of this base. And now the fiber will be all diffeomorphisms which preserve this very volume form mu. Now, if I take another volume form, for instance, it will be rho here, then the fiber will not be, of course, the diffeomorphisms which preserve rho, because, for instance, the identity will be sitting here.
So you're going to compressible hydrodynamics.
Yes, exactly. But slowly. So this is another volume form. So the fiber over that is, it consists of all diffeomorphisms. For instance, phi that move the fixed reference volume form mu to this volume form rho. So this is the set of cassettes, and that's our kind of starting picture. Now,
Rho have compact support.
yeah, let's say the term is just compact manifold. Yeah, otherwise we'll have to.
Rho is it's strictly positive everywhere, or can it have compact support?
No, I would like it to be strictly positive everywhere.
Strictly positive.
Strictly positive, yes. So that we would have a Moser theorem that everything is transitively acting on the base.
Okay.
So every volume form is moved to any other volume form,
Correct.
provided that. So since we have the total mass is the same. Yeah. Okay, so that's the setting, and now one can actually. So just maybe a word of caution. So if we have, for instance, one-dimensional manifold M, then the base consists of all functions, essentially positive functions with fixed normalization, while the fiber is just rotations. For instance, if we have a circle, if we have the two-dimensional manifold, then roughly fiber and the base are of the same dimension, like functions of two variables. And if the dimension of the manifold M becomes larger, 3 and larger, then the fiber consists of all divergence 3, roughly like all divergence 3 vector field, just one functional condition, while the base consists of just smooth functions like densities. So with dimension 3 and higher, the fiber becomes much larger than the base. That's kind of the idea. Now we fix a metric on this whole group of all diffeomorphisms. So an easy way to think about this is for a flat manifold M. So suppose that M is flat like Rn or n-dimensional torus. And then I'm thinking of diffeomorphism, at least close to the identity, as a vector function. So it takes one point in Rn to another point in Rn. And then we just put the L2 metric on this vector functions. So that's a flat metric. It's essentially just a pre-Hilbert space. But in general, it is given just by this formula that is here. And one can see that this metric is not right invariant, but it is right invariant if we act only by volume preserving diffeomorphisms. In general, when we act by diffeomorphisms, then there will be the determinant of the corresponding diffeomorphism coming out as a factor here. And if it is identically equal to 1, then it will be an invariant metric. So it's invariant only with respect to volume preserving diffeomorphisms. So why it is a natural metric to consider? It turns out that, again, I have this very setting here. It's the flat L2 metric on this space of all diffeomorphisms, which is invariant with respect to the action of only divergence 3 vector fields. Notice that if we restrict this metric to the fiber, this it will be exactly Arnold's metric that I started with. It will be the L2 invariant metric on all volume preserving diffeomorphisms.
Can you repeat the definition of the metric? Just what is the
Okay,
you
so
don't have metric.
maybe it's so if you think of so this is the space of all diffeomorphisms, and this is volume preserving diffeomorphisms.
Yeah, but
Now I take diffeomorphisms which depends on so G will be for every T. So this will be a path parameterized by T. It will be setting, for instance, Rn to Rn. So and what I'm just taking, I'm just saying that if I would like to take
Rn, where is Rn?
the
Sorry, where is Rn? Rn, what is
so
Rn?
manifold M is Rn or Tn. That's just a flat manifold. So
So you have a
so
metric.
G just sends a point X to G of X.
So then you have metric essentially on M, right?
Yes. I have a metric on M, and now I just define the metric on G. So by just saying that I take the derivative of G,
Yes.
and then take the integral.
That's fine.
And then I also from 0 to 1, if I would like to take the length of the path, then I also integrate with respect to T. So this is the metric. And so it's just written symbolically in this form over here.
Is the measure mu, is that the thing you have?
The original measure, the reference measure that I started
So
with.
it's not really, you have a metric on M, but mu is not related to the metric on.
Mu is not related to the metric on M. But kind of in principle, I can take the Riemannian measure, and for simplicity, I can actually fix this. But in general, one can develop the whole theory without actually this relation. So there exists some metric upstairs. Now, maybe it's worth since talk of Alexei, there was some proof, so I'll also give a one-line proof. What are geodesics with respect to this metric? Of course, it is just a flat space, so geodesics are straight lines. So what does it mean? It means that when so this is, I introduce the velocity vector field just as is a vector field, which is tangent to the motion of particles. So in some sense, it traces every particle x. And then the acceleration of g that I have to take a derivative of the derivative. So I have to take the derivative of this formula. And then since t appears twice here, it is just the chain rule that I have to differentiate with respect to t, v, and also with respect to x, and then g with respect to t again. So it will be again v over here. So what we'll see is this material derivative appearing as the acceleration. It's computation of the acceleration. So if it is equal to 0, it means that this is a straight line, and this is exactly what's called the Burger's in this Burger's equation, when every particle is flying along a geodesic with the same velocity, and the equation describes how the corresponding velocity field changes. But if it is the Euler equation itself, now has this form. So the acceleration is just given by the gradient of a certain function, by the pressure function up to a sign, and it exactly means that acceleration is L2 orthogonal to all divergence free vector fields. That's exactly one of definitions of geodesics. So when a curve on the manifold has acceleration, which is everywhere orthogonal to the submanifold, so it's actually another proof for the flat case of Arnold's theorem that I started with, that the motion of the Euler equation is nothing but the equation of a geodesic flow on the subset of volume preserving diffeomorphisms among all diffeomorphisms. So it just emphasizes that this point of view, when we think about the whole group of diffeomorphisms, is convenient and kind of it's useful here. Okay. Why I brought this up? Just because of this result by Felix Otto of 2000, that it turns out that the natural projection that I started with, so from diffeomorphisms, we just see how they act on volume forms. It turns out that it is a Riemannian submersion. So what is this? So first of all, so I mentioned this picture that we had here. So we have all diffeomorphisms, and we project them to densities, to the space of densities on the manifold M. So suppose that I have it turns out that on the space of densities also there exists a natural metric. It is called Wasserstein-Wasserstein metric. So what is it? Instead of describing the metric, it's actually this metric has a Riemannian origin. I will describe the corresponding distance between two densities. So suppose that if I have two densities mu and rho, then the distance, this Kantarovich-Wasserstein distance squared, is defined as follows. So by definition, it is the following quantity. So suppose that I have a manifold M, and this will be volume form mu, and this will be the volume form rho. So I take a point X, and by diffeomorphism phi, I send it to phi of X. Then I would like to measure how far I move this point. So I take the distance between X and phi of X. Let's take distance squared. Now I would like to take the average value of how far I move the point. So in other words, I take the integral over M with help of the measure mu. So this is how far every diffeomorphism just moves points around. And now I would like to take the infimum among all possible diffeomorphisms phi, which do the job, which move one measure to the other. So, and this will be the distance between mu and rho. So that's explains wait a second. Yes. So this is the Wasserstein distance that I just explained. And now it turns out that the projection map is nothing but the Riemannian submersion, which means that one can actually there exists a one-to-one correspondence between geodesics on the base and horizontal geodesics in the ambient space. So we just have seen that horizontal geodesics are easy to describe. They're just solutions of the Burger's equation, and the geodesics on the base are solutions of the optimal mass transport problem. So in this picture, one can relate various notions that appear. So in fluid dynamics. So in a sense, now one can see that we have mass transport problems on the base, fluid dynamics of incompressible fluid in the fiber, and in general, we have the Burger's dynamics on the whole diffeomorphism group. Now I would like to move on slightly to a seemingly different problem. So the problem of description of the motion of vertex sheets. So vertex sheets these are objects that have jump discontinuities of the velocity. So they naturally appear, for instance, when the flow passes an airplane wing. So in this setting, the Euler equation. So for instance, I have the velocity field, which is split on a manifold M, which is split by a hypersurface, and on this, it's for instance splits. The hypersurface splits into positive and negative part, into two parts, the corresponding manifold. We have velocity field in one component, and in the other component, they must have the same normal component, so that in the next moment we do not have any whatever vacuum appearing instead of the vertex sheet, but they can have the this jump discontinuity of the tangential component here. So the corresponding Euler equation now consists of two parts. It is just the standard Euler equation on the plus part. On the minus part, the vertex sheet itself is moved by the normal component they have the same normal component I just mentioned, and the pressure function is continuous through the vertex sheet. So it turns out that, and this was discovered by Loschke and Otta, that there exists a natural metric on the space of vertex sheet. So so this let's look at so what is the space of vertex sheet? So we look at hypersurfaces on our manifold of given topological type that that are diffeomorphic to each other and bound some fixed volume in M. So it's the same volume that is bounded. And then one can define a metric on them in the following sense. So suppose that I have suppose that I have a hypersurface, and I would like to describe how to measure a vector field which moves this hypersurface somehow. So suppose that I have it's a small perturbation. So this will be a vector field V on the space of vertex sheets. So this is the space vertex sheets, and the surface gamma is a point in the space of vertex sheets. So this is the surface, a hypersurface in M. And now I move this. So I would like to measure a velocity vector to this hypersurface. Now, so the small perturbation of gamma means that it is a vector field which is attached to gamma in the physical manifold M. And now I would like to assign a number, its length. So I would like to realize this very small perturbation by the global vector field in the whole space. This will be the vector field U, which is divergence free, and it is exactly this vector field V on gamma. And then I take infimum over all vector fields in the ambient manifold which realize this very small perturbation of gamma. So this will be a metric, And now the statement of Loschke and Otte is that the corresponding geodesics with respect to this metric on the space of vertex sheets, they describe exactly, so geodesics describe the motion, those very equations that I just mentioned here. So they describe the motion of vertex sheets for incompressible flows given by globally potential fields outside of these vertex sheets.
Is it obvious that it's not zero?
I will. It is non-zero because it is bounded below by Wasserstein metric. I will mention this a little bit later. But it looks like again we have some infinite dimensional space of vertex sheets. It has the equations have kind of hydrodynamic this geodesic origin. And the question is how it is related to Arnold's approach, where also we have kind of geodesics on infinite dimensional space, but here we don't have clearly any kind of natural group. So how to relate these two approaches? So there exists the following heuristic point of view, which is closely related to that very Riemannian submersion picture that I described several minutes ago. Namely, before we had this projection of densities of diffeomorphisms to densities, but now we will replace it instead of all diffeomorphisms, we have volume preserving diffeomorphisms, and instead of densities, the base now will be vertex sheets. So now this will be the space of vertex sheets. So gamma will be just one point in this space. Now the fiber over gamma will be the space of all volume preserving diffeomorphisms which preserve that very gamma. And now if I have a fiber over gamma tilde, then it will be all diffeomorphisms which move gamma to gamma tilde. So that's exactly the same projection picture that we had before. So we have L2 metric upstairs, that very Arnold metric on all volume preserving diffeomorphisms on this now group of mu preserving diffeomorphisms. And I claim that the space of all vertex sheets, the metric that we defined on this space is exactly such that this very metric that I mentioned before is exactly such that this becomes Riemannian submersion by the very definition of this metric. So this means that indeed horizontal geodesics will be projecting to the geodesics on the base, and that explains the result of Loschke and Otte. Unfortunately, this picture doesn't work. So it's a natural kind of Riemannian submersion picture. It doesn't work for the reason that the fibers, as a matter of fact, there is no clear splitting into horizontal and vertical spaces. It turns out that fibers are L2 dense. So there should be some different approach. And it turns out that natural way of dealing with this is to define what's called multi-phase fluids. And instead of group, we have to move to groupoids. So, so first of all, what are multi-phase fluids, or more generally what's called generalized flows? So a multi-phase fluid consists of several or maybe even continuum fractions that can freely penetrate through each other without resistance and are constrained by conservation of the total volume. So we would like in total to have a volume preserving multi-phase fluid. So one should kind of imagine that what happens is that every particle, for instance, could split into a cloud of particles that kind of go through each other. Or if, for instance, this is a diffeomorphism, rather a map of a segment where two halves of this segment just change their places. So this is a what's called the two-phase flow. So one part of the segment goes to the left and the other goes to the right. So through every point there exists kind of two flows simultaneously. So trajectories of particles. Oops. In this one-dimensional case, the either we have a continuum of phases or two-phase flow. When exchange this segment, exchange the two halves of the segment. That's what picture suggested by Schneerman. So it turns out that in general, when we have a multi-phase flow, so we have several densities of n phases. You can think of two phases, for instance, of fluid, and then they each of the phases has its own equation. The corresponding density is moved by the continuity equation of its own velocity field. But the pressure is common for all phases, so it acts simultaneously. So that's an example that you have, for instance.
Make one little comment. If I remember correctly, the hydrodynamic equation, the gradient of P should be divided by the density, and you never write it.
Right. It will not be divided here. It is a multi-phase fluid. It's not compressible fluid. It's a different story.
Compressible fluid you also did not divide.
I didn't write the equations of compressible fluid yet, but I will.
Okay.
If we have time. But this is not a compressible fluid equation. That's what I emphasize. So this is a multi-phase fluid, and then you do not have to divide. I mean, you should not divide by the fluid. You have this condition that the sum of the densities. This is a very important constraint that, in total, every fluid component moves on its own, but they have this total constraint that the sum of the volumes is the total volume. So, for instance, I'll liquid and gas bubbles. Now, think of when you think of groupoid, you could think of a fluid with moving boundary. So I mentioned before that the picture proposed by Arnold is very universal. It covers a lot of cases, but in some sense, we were kind of hypnotized by the beauty of this picture. But it works when you have a group acting on our in our system. But for instance, there are many physical mechanical systems when you do not have group. For instance, you have a fluid with dynamic boundary. So you have a fluid drop and it moves to another place. You cannot make a composition of such diffeomorphisms unless you have the target which coincides with the source of the next map. Then you can compose them. That's exactly what's called the groupoid symmetry or groupoid structure. And in this case, we introduce groupoid type structure behind this fluid. Namely, this is natural to call the multi-phase groupoid. So it's so the base will consist of several densities, which are constrained by the condition that the total sum of them is equal to a fixed density, and they are all positive. So they so of course we cannot change the mass of each fraction. It is some given constant. And the groupoid consists of several diffeomorphisms, so n diffeomorphisms. So each diffeomorphism.
Sorry, density is not a density of a fluid. It's just some density
The component.
of the component.
Of the component. So you have several phases. And so, for instance, this is mu1 and so on, mu n is the components, and these are diffeomorphisms. So they act and they map the corresponding components to the new components. So they are primed over here. And then you can you have a natural composition law. So then the diffeomorphisms are composed, and then you kind of it's a forgetful map. Mu is mapped to mu prime is mapped to mu double prime, and then you keep only the composition and the initial and final densities. So that's the groupoid structure. It has a natural, example of this groupoid is exactly the picture with vertex sheets that I mentioned before. So now we think of two densities. One of them is just an indicator density of the plus component, and the other is of the minus component. And of course, the total sum is fixed density. And this way we'll trace how the vertex sheet is moving like this. So it is just a particular limiting case of that very groupoid. So there exists a natural space of infinitesimal objects that is called algebroid that essentially consists of vector fields corresponding to each particular fraction, to each particular phase. And they have their own constraint that the total sum of the Lie derivatives of the corresponding fractions is equal to 0. And this exactly is a generalization of incompressible fluid on the manifold. And in case of indicator densities, it generalizes the vertex sheets that I mentioned before. So then our theorem with Anton is that it turns out that these very equations that describe this multi-phase flow are groupoid Euler-Arnold equations corresponding to L2 metric on the algebroid. So it turns out that one can develop the corresponding formalism of Euler-Arnold equations in this more general context, which describes vertex sheets, moving boundary, and so on, in multi-phase fluids. And in particular, now it indeed describes the corresponding picture of suggested by Loshkin and gives this kind of universal point of view. I would just like to mention that there exists a Hamiltonian version of that when we move to the dual object, just like for Lie algebras, we move to dual of Lie algebras, and then it's Lie Poisson equations. One can also consider continuum of fractions. So when we have the index is not discrete I from 1 to n, but just belongs to some probability space, measure space A, and these are the corresponding equations written by Jan Brinier. So it turns out that now they have this groupoid understandings that they can be viewed as Euler-Arnold equations on the groupoid of continuum phases. And there exists an analog of the Hodge decomposition in this case, but we'll just skip this, and the computation of the corresponding geodesics. Maybe just a quick remark here is that it turns out that the metric, one can also introduce the metric on the vertex sheets that is that I mentioned before, and it turns out that there exists a more general metric on the base of that groupoid. Well, there exists a natural inequality that since here we move one vertex sheet to another by volume preserving diffeomorphisms, then it's the distance is bounded below by the densities when we just put indicator density inside one of the domains by Wasserstein distance, because Wasserstein doesn't require us to move by volume preserving diffeomorphism. So because of that, the metric is non-degenerated. That's your question. There are some open questions that in this domain. For instance, it would be very interesting to study geometric properties of this vorticity metric on the space of vertex sheets. And in particular, for instance, describe paratropic multi-phase fluids. So when we allow compressibility, I will comment on that probably. I have like several minutes.
Yeah, still like maybe 4 minutes.
Okay, good. Yeah. And there are some other questions. For instance, one can develop a similar theory, and it will be interesting to develop, but kind of it's quite an open question. H1 geometry. I mentioned before that Arnold's point of view allowed various metrics, and H1 also leads to interesting equations of shallow water. So that's an open question again. Maybe just a quick word about barotropic fluids. There's an equation that you like. So we have, if we have Euler equation for a barotropic fluid, then the corresponding material derivative is supplemented by gradient of a pressure function where pressure depends only on the density. And of course, we have to have divide by density here, and we have incompressibility, continuity equation on densities. So here there is this state equation for the density function. And it's a very practical set of equations because it describes, for instance, the motion of an Earth atmosphere and so on. So it turns out that in this case, that very picture with Riemannian submersion allows one to give a description of the corresponding barotropic fluids, namely, they are not geodesics anymore, but they are solutions of the Newton equation. Namely, one can introduce not only so Lagrangian is now given not only by kinetic energy, but also by we have to introduce potential. And potential energy is a fluid is a function which is defined on the base. It depends on the density only, but one can lift this function to this whole group of all diffeomorphisms, and then the corresponding Hamiltonian will be the sum of kinetic and potential energy, and the corresponding equations will be exactly those equations of the barotropic fluid. This is the result of Smolentsov back of 1979, and we developed this in this setting of Riemannian submersion. Maybe just one last word about this is that the H1 geometry, for instance, for the group of diffeomorphisms of a circle of the Virasoro group, leads to several interesting equations. For instance, not only Burgers, but this is for L2, but for H1, one has Kamasa-Holm. For H1 dot, one has Hunter-Sexton equation. And it leads to an interesting geometry in more general setting. I would like to mention that there was a beautiful paper by Penskoy and Sasha. When was that? 20 some years ago. That it turns out that discrete systems on the Virasoro group leads to the same set of equations. Also Kamasa-Holm, Hunter-Sexton, and KdV under rather general assumptions. So in general, this H1 geometry on the group of diffeomorphisms here leads not to the Wasserstein geometry, not to the geometry of optimal mass transport, but to what's called information geometry. They are called Fisher-Wasserstein, Fisher-Rao metrics, and it's kind of an analog of the Wasserstein metric here. It is closely related to Madelung transform. So again, I've mentioned several open questions, and these are the literature that was used in the talk. And happy birthday.